All right, welcome back, everybody. Lecture video number 3 here for chapter 5. Not a whole lot of stuff to cover here because it's mostly going to be rooted in, actually doing sample problems in class. So I'm just going to kind of quickly talk through these slides, at least these first two. But these first two slides particularly are about some really big concepts that we're going to talk about in chapter 5 here. And this first one here is all about writing formulas for ionic compounds. So it's essentially saying, hey, how do I take the name of this compound, sodium chloride, the words sodium chloride, and convert those words into an actual formula? That's essentially what this slide is all about, okay? 4 steps, 4 rules associated with it, so let's get right into them, okay? First one here, determine the symbols for the ions present in the compound. That's pretty straightforward, right? We've kind of already done that, kind of already gotten our feet wet with that a little bit recently, right? Determining the symbols, right? So when you've read the word potassium ion, you guys know instantly that potassium is a capital K. You guys know that calcium is a capital Ca. You guys know that sodium is a capital Na. Chlorine is a Cl, etc., right? So determine the symbols for the ions present. Now, a little bit of a catch here is that whenever we're talking about transition metals have a little bit of a different and added layer to them, right? And it's all about these Roman numerals present here. So if you remember, transition metals are all of the elements in the dead center. It's that massive kind of chunk in the dead center of the periodic table from group 3 all the way to group 12, right? So it's that big chunk right in the dead center, group 3 to group 12 there. Now, what this is saying is that whenever you see a Roman numeral attached to the name of any of these transition metals, that Roman numeral is indicative of the charge, right? So there are other Roman numerals present here, right? So if you have a Roman numeral 1, for example, Roman numeral 2, Roman numeral 3, Roman numeral 4, which is IV, Roman numeral 5, Roman numeral 6, Roman numeral 7, which is another V with an I, Roman numeral 8, which is V, I. Okay, and that's pretty much all you really need to know. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8. We don't really need to worry going much farther than that with our Roman numerals, okay? But again, that is what our Roman numerals look like, right? And those are going to be indicative of the charge. So if you ever see a Roman numeral 2, 3, whatever, that Roman numeral is the charge. So if you see a Roman numeral 2, it's a +2. If you see a Roman numeral 4, it's a +4, right? Number 2, draw a picture to ensure that the total charge is equal to 0. Right, we kind of have some experience doing that to a degree in terms of the total charge needing to be equal to 0. We did that in class the other day with our determining charges on ions in compounds. And I'll show you how to do this whole picture thing. It's going to be one of the sample problems that we do in class when I see you next. Okay. Step 3, crisscross the superscripts to determine the formula. I'll talk more about superscripts and this crisscross rule or crisscross method. We do some example problems, but some things to keep in mind with step 3, leave off any subscripts of 1. Again, recognizing that our least favorite number in chemistry is the number 1, right? So we want to make sure that we're leaving off 1 wherever it's possible. And then ensure that we have the simplest ratio as well, right? So if you have a ratio of, let's say, 4 atoms to for every 6 atoms you have, right? That's not a simplified ratio, right? You guys have learned in the past, probably as far back as some late elementary school, 4th, 5th grade, maybe even some middle school math there, how to simplify ratios, right? If we have a ratio of 4 to 6, that ratio of 4 to 6 can actually be simplified to just 2 to 3, okay? And then lastly, number 4, double check that the total charge is equal to 0. All right, got to make sure all your charges associated with every piece of your formula is equal to 0, plain and simple. All right. Next up here is the opposite of that, going in the opposite direction. Okay, naming ionic compounds. Well, again, this previous slide here tells us how to go from the name of a compound to the formula. This slide tells us to go in the reverse, how to take the formula and go into the name and transition that formula into the name. Okay, it utilizes what's known as the IUPAC naming system. And here's 2 basic rules of thumb, and it's actually different for whether it's a cation or positive ion, and it's different for any of our anions or negative ions here. Okay, so for the cation, it just plain and simple has the same name as the atom. Okay, so if we're talking about the magnesium ion, that's because it comes from the magnesium atom. Plain and simple, nothing crazy here. So magnesium stays magnesium because magnesium is going to be a plus or a positive. Okay, sodium stays the word sodium because it's not going to change. It's a positive ion, right? So if it's a positive ion, don't change the name at all. Stay as it is, as you see it on the periodic table. For transition metals, just of course, same thing as we just discussed. If you see a transition metal, just make sure you have the Roman numeral present in parentheses to indicate the charge of it, right? So if it's the iron +3, that +3 needs to convert into an Fe for iron and then a Roman numeral 3 in parentheses to show that you're using the +3 charge for iron. And that's it. Those are the only two rules for positive ions. Negative ions, however, there is a name change required for these guys, okay? And it's actually pretty simple. It's something that we saw recently with one of our more recent classes not too long ago, right? We saw words like fluoride, and we saw words like oxide and nitride. Well, that's because all of these negatively charged ions here, these anions, utilize an IDE ending. Okay, this IDE ending right here, okay? The anion has the same name as the atom, but with the IDE ending instead. So, for example, we've got something like chlorine. Chlorine on the periodic table is ending with INE. But what happens is we remove the INE ending and we replace it with the IDE ending, allowing it to turn from chlorine to chloride. Same thing with oxygen, right? But there's a little bit more chopping involved here, right? Oxygen removes the last four letters here, YGEN, and gives us oxide, IDE, plain and simple, okay? Nitrogen, same deal. We remove the last handful of letters here, OGEN, goodbye, and we add the IDE ending once again, okay? So the ending here that you have to know and love is IDE, IDE, and IDE, okay? That is the ending you use for negative ions only. Again, we're not changing any positive ions, only if it is a negative ion. That's it. Okay. Moving away from naming, just to kind of finalize some, basic things for this chapter, let's talk about some properties of ionic compounds, right? For the most part, ionic compounds have definite crystalline pattern and structure to them. They have a very, very, very high boiling and very high melting point. Okay, these ionic compounds and these ionic solids are pretty brittle as well, right? Think of your table salt, for example, right? Table salt is like this, white crystalline looking, substance that's very, very brittle, right? It's very easy to smash and break table salt, right? NaCl. So it's very brittle, right? And that's pretty common for all ionic compounds as well. Now the solids themselves, right? So solid salt does not conduct electricity, but whenever you have a substance that is an ionic compound that you dissolve in water, it's going to form what's known as an electrolyte, and it actually will conduct electricity. It's actually really, really cool. So if you take, for example, sodium chloride, right? Actual sodium chloride salt, and you try and conduct electricity through the solid salt, not going to work. But let's say you take a couple of scoops of sodium chloride and you throw it into some water and you stir in and create a solution, right? A homogeneous solution. We learned about homogeneous solutions a while ago, right? If you create a homogeneous solution of salt and water to create salt water, that salt water will actually conduct electricity through it. It's actually pretty cool. Now some symbolism for states of matter, right? Things we're all relatively familiar with, right? We've seen them before in the past. Right, if you've got solid sodium chloride, you have this S here, where this S is going to represent solid. Liquid sodium chloride is going to be a liquid, right, a lowercase l in parentheses. If you have a G in parentheses, a lowercase g in parentheses, that means it's going to be a gas, right, sodium chloride gas. AQ, right, leading into that aqueous we've talked about in the past there, right, so aqueous. So solid, liquid, gas, and aqueous are our symbolisms for states of matter. Just kind of brushing up on those because we haven't talked about them in a little while. Metal hydrides, for example, right? Metal hydrides are compounds that form between hydrogen and an alkali metal or alkali earth metal, right? Alkali metal being group 1 and alkali earth metal being group number 2. Hydrogen gains an electron and becomes a -1 ion. So some examples like this, NaH and MgH2, right? In this case here, Na is the positive ion and H is the minus ion. In this case here, Mg is the positive ion again, and H is the negative ion. So these are some metal hydrides where hydrogen, instead of acting like a +1, like a metal, it sometimes will actually not act like a metal. It will act like a non-metal that it well and truly is, okay? Hydrates, okay? We're going to do a couple of really cool labs regarding hydrates here. Hydrates are ionic compounds with water built into the crystal structure, right? So something like this, for example, copper sulfate, water, right? Copper sulfate H2O is essentially called copper hydrate pentahydrate, and it basically has water molecules trapped inside of the crystalline structure of the copper sulfate. It actually has an added weight to it because those water molecules are trapped. It feels very dry when you touch this copper sulfate. We're going to see copper sulfate a bunch in the future, especially in labs and whatnot. And this copper sulfate stuff is really, really cool, right? It's actually got water molecules trapped inside of the crystalline structure of them. But again, the water or the copper sulfate powder is a powder. It's a solid, right? So it's not wet. It's a literal solid powder, but just has water molecules trapped inside of those different molecules. Okay. And the last thing we're going to talk about here is known as metallic bonding. Again, I very, very briefly mentioned metallic bonding at the very, very start of this chapter here, but I'm talking about it very, very briefly again at the end of the chapter because it doesn't really matter too much. We don't really talk too much about it in this unit. But in this type of bonding, metals form cations surrounded by a sea of electrons. This sea of electrons makes metals good conductors of heat and electricity, right? So each of these red circles here with the positive symbols here are these metal cations, right? Again, cation, that word, C-A-T-I-O-N, is just a word of saying, hey, this is a metal positive ion being formed. Cation is a positive ion. All around these positive cations here, these red circles with the positive symbols here, all around them are a bunch of negatively charged electrons, creating this sea of electrons. And that's what makes all these different metals like copper and nickel and all these other metals super, super, super good conductors of both heat and electricity, right? Because they create these metallic bonds between each other with the sea of electrons all throughout all of them, okay? And that's all I've got for you guys, so I will see you next class. Thanks. Just kidding, I forgot I have one more slide here. So let's get right to this slide here. The sea of electrons in a metallic bonding explains the properties of metals as well, right? So we've talked kind of briefly about metals and their properties a couple of units ago, about how metals are basically malleable, right? So whenever you kind of hammer them out, you can they're malleable. They can be hammered into sheets. They are ductile, which means they can be drawn into wires, right? They're very, very easy to be manipulated and whatnot when you add an external force to them. But again, just by manipulating them and flattening them out doesn't mean that they lose out on anything, right? They just essentially are deformed, like it shows here in this diagram here. And then an alloy. You might have heard of alloys before, but alloys are mixtures of elements that have metallic properties to them, right? So alloys of steel, for example, right? Maybe there's a steel alloy that mixes two different elements together that are metals to create an alloy, a stronger mixture of metals to give rise to something like an alloy. Okay, so now we are ending up with this video. Okay, so again, I will see you next class. Thanks.